Hello everyone, welcome to UnQuestionIt. In this video series, I'll be making videos for competitive exams, specifically for physics. I intend to cover each topic syllabus wise so that we don't miss anything. Stay tuned to my channel. If you like the video, then please subscribe the channel for more videos coming down the pipeline. So let's get started. Today's topic is dimensional analysis. In this video, we'll be discussing these subtopics of the dimensional analysis. So first we'll go through what the units are, then the international system of units, dimensions of physical quantities, dimensional formulae and dimensional equations, dimensional analysis and its application, which has two parts: checking the dimensional consistency of the equations and deducing relation among the physical quantities. So let's see what the units are. So in the real world, we want to compare one thing to other things. So the measurement of any physical quantity involves the comparison with a certain basic arbitrarily chosen internationally accepted reference, which is called standard unit. The result of a measurement of a physical quantity is expressed by a number accompanied by the units. So let's say this internationally accepted reference is important because in India, let's say we want to say 1 meter, and when we go to US it shouldn't be like 100 meters or something. So this should be internationally accepted, and to make the comparison between two different lengths, we want to make it with the same unit. So like this is 1 meter and this is 2 meter, then you can say that this length is double of this meter just by the fact that they have the same units. Okay. Although the number of physical quantities appears to be very large, like the velocity, force and all, we need only a limited number of units for expressing all the physical quantities, since they are interrelated with one another. The units of fundamental or base quantities are called fundamental or base units. So the fundamental or base units are the most fundamental units which will be required throughout our study. The units of all other physical quantities can be expressed as a combination of the base units. Such units obtained for the derived quantities are called derived units. So like velocity, what is the unit of velocity? It will be something like meter per second. So it is being derived from meter and second. So for this velocity, it is called the derived unit. So a complete set of unit with both base unit and derived unit is also called as the system of units. Okay. So let's see what is the international convention of the units. So earlier time, scientists of different countries were using different system units for measurement. Three such systems, which were the CGS, FPS and the MKS system. The base unit for the length, mass and time in these systems were as follows. So in the CGS, the length was measured as centimeter, the mass as the gram and the time as the second. In the FPS, the length was measured as foot, the weight was measured as pound and the time as second. In the MKS, it was meter, kilogram and second. So these are the system of units which were used for the different countries. Okay. So the system of units which is at present internationally accepted for measurement is called the International System of Units, also abbreviated as SI. So we normally nowadays deal with SI units because SI units use decimal systems. Conversion within the systems are quite simple and convenient. Okay. In SI there are 7 base units, which you can see here. Beside the 7 base units, there are 2 more units which we measure as the angle. So this angle like d theta, and this type of angle is called the solid angle. So these are the 2 different units apart from these 7 base units. Okay. So length has the meter, mass as the kilogram, time as second, electric current as ampere, temperature as the Kelvin, amount of substance is mole, and luminosity as the candela. Okay. And the angle is measured as the arc length divided by the radius, which the unit as the radian, and the solid angle is measured as the area divided by r square, the unit is steradian. Fine. So in total we have 9, but mostly used are these 3 are the mostly used in mechanics. Fine. Okay. So now since this study is regarding the dimensional analysis, so let's get back to the dimensions. What are the dimensions of the physical quantities? So the nature of physical quantity is described by its dimension. All the physical quantities represented by derived units can be expressed in terms of some combination of 7 fundamental or base quantities. Like we described that mass was the fundamental unit, meters, and the second was also the fundamental unit. But if you want to write the unit for the velocity, you have to make some form of this, which is meter per second. So this is called the derived unit, which is the combination of base units. Okay. So we shall call these base quantities as the 7 dimension of the physical world, which we denote with the square brackets. So length has the dimension L, mass has the dimension m, time has the dimension t, electric current A, thermodynamic temperature K, luminous intensity CD, and amount of substance as mole. The dimensions of physical quantities are the powers to which the base quantities are raised to represent that quantity. Okay, so we'll see this concept later. Okay, so in mechanics, all the quantities can be written in terms of length, mass, and time. For example, let's take the volume. So volume occupied by an object is expressed as the product of length, breadth, and height, or you can say the 3 lengths. So if we take a cube, so this also has the dimension of length, this also has the dimension of length, this also has the dimension of length, and volume is the multiplication of all the 3s. So now you can see that what is the dimension of volume? L into L into L, which is L cube. So as the dimension of volume is independent of mass and time, it is said to possess zero dimension in mass, 0 dimension in time, and 3 dimension in length. Okay, so if we write the unit of volume as m to the power 0, L to the power 3, and T to the power 0, so it has 0 dimension in mass, 0 dimension in time, but 3 dimension in length. Okay, so similarly, let's see for force. So the force is mass into acceleration, and then acceleration can be broken down into length upon time square. Okay, so what is the dimension for the mass? That is m. And what is the dimension for length? L. What is the dimension for t? Is t. Okay, and since there is a time square, we put as t square. So when we combine all this, we have the dimension of the force as mlt minus 2. So the force has one dimension in mass, one dimension in length, and minus 2 dimension in time. Okay, so note that this is the type of representation. The magnitude are not considered. So since we are dealing just with the dimension, the magnitudes are not considered. It is the quality of the type of the physical quantity that enters. Thus a change in velocity, initial velocity, average velocity, final velocity, and the speed all are equivalent in this context. Since all the quantities can be expressed as length by time, their dimension is lt minus 1. Fine. Okay. So now let's see what are the dimensional formula and dimensional equation. The expression which shows how and which of the base quantity represents the dimensions of physical quantity is called the dimensional formula of the given quantity. Okay. For example, the dimensional formula of the volume is m0 L3 T0, and that of speed will be, or the velocity, or the initial or final speed will be m0 Lt minus 1. Similarly, m0 Lt minus 2 is the dimensional formula for the acceleration, ml minus 3 T0 is for the mass density. So an equation obtained by equating a physical quantity with its dimensional formula is called the dimensional equation of the physical quantity. Okay, so we'll be using this a lot in the coming slides, and this is very helpful. You will see in the upcoming slides. So thus the dimensional equations are the equations which represent the dimension of the physical quantity in terms of the base quantities. For example, we have seen for volume it's L to the power 3, but we can write it as m0 because it doesn't matter, m0 is essentially no dimension. So m0 L3 T0 for volume. For velocity it's Lt minus 1. For force it's mlt minus 2. For mass density, so mass density is the mass divided by volume, so it's ml minus 3. Okay, fine. So now we are going to use this dimensional equation to analyze and see its application. So the first one is checking the dimensional consistency of the equation. This is very helpful if you want to see that the formula is correct or not in the dimensional sense. So magnitude of the physical quantities may be added together or subtracted from one another only if they have the same dimensions. Okay. In other words, we can add or subtract similar physical quantities. Thus, velocity cannot be added to force, or an electric current cannot be subtracted for thermodynamic temperature. So, in order to add electric current to something, that should also be of the dimension of the current itself. This simple principle is called the principle of homogeneity of the dimensions in an equation. Is extremely useful in checking the correctness of the equation. If the dimension of all the terms are not same, the equation is wrong, and this is the important point. So if you see that one term is being added to another and their dimensions are not same, the equation is wrong. Hence, if we derive an expression for length of an object, regardless of the symbol appearing in original mathematical relation, when all the individual dimensions are simplified, the remaining dimension must be that of length. This we'll see by one equation as an example in the next slide. Similarly, if we derive an equation of speed, the dimension on the both of the side of equation when simplified must be of Lt minus 1, that is the dimension of velocity. So dimensions are customarily used as the preliminary test of the consistency of an equation when there is some doubt about the correctness of the equation. However, the dimensional consistency does not guarantee correct equation. It is uncertain to extent of dimensionless quantities or functions. Okay, so I'll also describe this in the next slide. So let's go to the next slide. Yeah, so now we can test our dimensional consistency or homogeneity of the equation. So here is the equation. For the distance traveled x traveled by a particle or body in time t, which starts from the position x0 with an initial velocity v0 at time t equals to 0, okay, and has uniform acceleration a along the direction of motion. So this is, you can see, is the second law of Newton. Okay, so since the initial position was x0, so we have added x0 there. So to check that this formula is dimensionally correct or not, let's see. So what is the dimension of x? Since this is the length, the dimension will be L. What is the dimension of x0? It is also L. What is the dimension of v0 t? v0 t is, so for v0 it's Lt minus 1, and for the time it's t. So when you multiply it, you will get L. It is also fine. What is the dimension of at square? We do not care for this half because it doesn't have any dimension. So we care about the at square, which has the dimension. Okay, so for a it's Lt minus 2, and for t square, time square is t square. So when you multiply, it's L. So this equation is dimensionally correct. Okay, so as each term on the right hand side of this equation has the same dimension, namely that of length, which is same as the dimension of the left hand side of the equation, hence this equation is dimensionally correct. Okay, now it may be noted that the test of consistency of dimensions tells us no more or less than the test of consistency of units, but has the advantage that we need not commit ourselves to a particular choice of units. We need not worry about convergence among multiple and submultiple of the units. Okay, so this line here, it may be borne in mind that if an equation fails this consistency test, it is proved wrong. So let's say instead of x0 here, or instead of v0 t here, if we have v0 t square here, so what will be the dimension of v0 t square? It will be Lt minus 1, and then t square as t square. So what it will be? It will be Lt. So now this Lt is not the same as L. So you see that this equation will be wrong directly. Okay, but if it passes, it is not proven right. Why it is not proven right? Let's see. So now we have the equation x equals to x0 plus vt or v0 t plus half a t square. Now let's say if this equation seems dimensionally correct, but if we remove half from here, still this equation is dimensionally correct. Okay, but as the value you see, you will be getting double of this term because you have removed half, so you will not be getting the correct position. So thus a dimensionally correct equation need not be actually an exact correct equation, but a dimensionally wrong, incorrect or inconsistent equation must be wrong. Fine. So let's see an example. So let us consider an equation half mv square, which is kinetic energy, is equals to mgh, which is the potential energy. M is the mass of the body, v is the velocity, g is the acceleration due to gravity, and h is the height. Now the question is, check whether this equation is dimensionally correct or not. So what is the dimension of the left hand side? So what is the dimension of m? It's m. What is the dimension of v square? It's lt minus 1 to the power 2. V is the velocity. Velocity is lt minus 1. If we multiply, we get ml2 t minus 2. Now let's go back to the right hand side. What is the dimension of m? It's m. The dimension of g. G is the acceleration. So acceleration has the dimension lt minus 2. And height is the dimension of L. So if we multiply, we get ml2 t minus 2. So since this LHS and RHS are equal, the dimensions are same, hence the equation is dimensionally correct. Okay. Now our next point of this analysis. So this is one of the most important one, because using this you can deduce the relationship between different physical quantities. So the method of dimensions can sometimes be used to deduce relation among the physical quantities. For this, we should know the dependency of the physical quantities on one another and consider it as the product type of dependence. Let us take an example. So you should know any physical quantity relation if you don't know exact relation, but what are the physical quantity it depends on. Also, it should be something of the product type. So let's see this exactly what it is by the example directly. So now consider a simple pendulum. So we have the simple pendulum. We know it oscillates like this. Okay. So this bob has the mass m. This has the length L. This has the gravity G. Fine. And we want to derive an expression for its time period. And it is given that this time period depends on all these three. Okay. Length, mass, and gravity. So what do we do? So we say that, okay, we don't know exact formula, but we know that it has some dependency. So let's say L to the power x. So the time period is some constant multiplied by L to the power x, G to the power y, M to the power z. Okay. Now what we are going to do, that we are going to write the dimensions of the left hand side and of the right hand side. So what is the dimension of right hand side? It's time. So the dimension of time is t1, and let's add L and M also, because if it is power 0 it doesn't matter, but it will be helpful. We'll see. Now what is the dimension of right hand side? K doesn't have any dimension because it's a constant dimensionless quantity. L has the dimension L, length, and to the power x. G has the dimension of the acceleration, that is Lt minus 2 and to the power y to match it with. M has the dimension M to the power z. Now if we take the simplify this, we will find L to the power x plus y, t to the power minus 2y, and to the power z. Okay, this is the dimension of left hand side and right hand side. Now what we have to do is we have to compare the powers on the LHS and RHS. So what is the dimensional power of L? It's x plus y here and 0 here. So x plus y will be 0. What is the power of t? Minus 2y here and 1 here. So minus 2y will be 1. And what is the power of M? It's z here and 0 here. So z will be 0. So if you simplify this, you will get x equals to half, y equals to minus half, and z equals to 0. Let's put all this into this equation. You will get t equals to k l to the power half g to the power minus half, or t equals to k under root l by g. Fine. You see that we have got almost the formula of the time period except this constant k. Okay, so we know that time period equals to 2 pi under root l by g. So this constant we can't get it from the dimensional analysis, but the relation we can get easily. So now note that the value of constant cannot be obtained by this dimensional method. Here it does not matter if some number multiplies the right side of the formula, because it does not affect its dimension, which is an important point to remember. Okay, so this is very powerful tool to deduce any physical relation of the quantities. Okay, so as a conclusion, we have that the dimensional analysis is very helpful in deducing relation among the independent physical quantities. However, the dimensionless constants cannot be obtained by this method. The method of dimensions can only test the dimensional validity, but not exact relationship between physical quantities in any equation. It does not distinguish between physical quantities having same dimensions. Okay, so this is the last slide of this video. So that's all for this video. I hope you like the video. Please hit like and also subscribe to my channel for further coming down the video